Hey guys, so today we are going to be talking about quicksort. This is a divide and conquer algorithm, which basically means that you divide the thing into multiple parts and then you work on those multiple parts. It's all about reducing the problem area or the problem size, which we'll talk about. And so yeah, it's pretty easy, and it's very easy to come up with really good real world analogies for this. So the typical explanation is you pick a pivot point from the array, and then that sort of acts has the area of division. Okay, and so based on that pivot, if something is in lower value than the pivot, it goes to the left, into the left side, you can say. Not like a tree though. Imagine it's like so. Imagine these two being like two buckets. It goes in the left bucket, and then the values greater than the pivot go in the right bucket. Okay, and then once it's separated out into those two buckets, you do the same thing to the contents of the buckets, right? So the subarray, the main array is broken up to subarrays, and then you run the same process on the subarrays. Okay. We'll talk about time complexity and stuff later on. So let's do an analogy. Okay, so the best analogy is with a deck of cards. All right, so let's say that you're gonna sort a deck of cards, and so let's say that you're gonna pick 7 as your pivot. Okay, 7 of hearts. It doesn't really matter. The value is what is important here. All right, so we're gonna go through the deck, and every card that is less than a 7, we're gonna put on the left side. And another deck on the left, and then every card that's greater than 7, we're going to put in another deck on the right. And then we're going to take those piles that we create, and we're going to do the same thing. We're going to choose pivots and then do the same thing. Right now, once those stacks are sorted, then we combine the MAC with the pivot going wherever it needs to go. That's the last step in the algorithm, is the placement of the pivot. Okay, so let's look at some pseudocode. This is pretty high level. This is pseudocode, super high level. So let's say that we have an initial array, right? Got 8, 3, 1, 7, 0, 10, 2. Okay, so let's say that we're going to select 2 as our pivot. This is just the last element. We're going to talk about pivot selection. It's pretty important. So just for now, we're picking the last element. Okay. So then we go through and we compare each element to the pivot, moving the smaller elements to the left and keeping the larger elements on the right. So after partitioning, we end up with this result, right? So we partitioned at 2, 1 and 0 are less than 2, so those go to the left, while 7, 8, 10, and 3, those are greater than 2, so those are all going to the right of the pivot, right? And then the pivot right into the right of the pivot. And so this is what it looks like. This is kind of, I got these backwards. So this is what it's going to look like after it's combined. And this is what it's going to kind of look like in its pieces, right? You're going to have left, pivot, and then a right, okay? So the algorithm is recursively applied, right? So on our left partition, we have 1 and 0, right? The pivot is 0, last element, and then the partition result is going to be 0, 1, okay? Then we go into the right partition and we do the same thing. Right, so in the right partition, we're going to select the pivot as 3 because it's the last one, and then the partition result is going to be 3, 7, 8, and 10. Okay, and then the final sorted array is we combine the sorted partitions. Right, so 0, 1, and then the pivot, and then the remainder, and then the right side. Now, pivot selection. This is the question that always comes up the most when I'm teaching about this. So in our code, we pick the last element in the array. This is straightforward. The reason I do this is because it's straightforward and ensures a clear, consistent process. And but the pivot selection can impact performance. Okay, so this is the code that we use in ours to select the last element in the array as the pivot. Okay, and so this is perfectly fine for demonstration purposes. Talking about the algorithm, interviews, and stuff like that. But in production, the pivot will matter. Okay, so I would say that the most common approach to selecting a pivot is to select a random element. This is because it reduces the likelihood of the worst case performance, which we'll talk about in a minute. And another common method is taking the it has a name, It's not the rule of thirds. It's something I don't remember, but yeah, basically what you do is you take the median of the first, middle, and last element, and then you select your element based on that value. So this is good because it's a good balance of simplicity and partitioning, but selecting selecting a pivot based off a random generated number, I mean, that ain't hard to do either. So can you always just choose the last element? Well, yeah, you can. You need to keep a couple of things in mind, though. Your best case scenario when selecting the last element is that the array splits evenly, right? Which, it depends on the data set and other factors. So, yeah, the worst case is when the pivot is the smallest or largest element. So this leads to heavily imbalanced partitions, right? So if you're not paying attention, and you pick the lowest value in the data set as your pivot, and it just happens to be on the end, it's not going to perform, right? So it really depends. It depends on the application and the context, right? And how well you can predict the composition of your data set. So performance. The best case is linear arithmetic time, right? And so at each level of recursion, the algorithm processes all the elements, right? And then the number of recursive levels is proportionate to log n. And so that's the array being halved at each step, right? So n represents the work done per level, all of the elements, and then log n represents kind of the levels of recursion. And so yeah, and the best case occurs when the pivot divides the array into two nearly identical halves. The more balanced the sides are, the more performant the algorithm is going to be. Now, the worst case scenario is quadratic time. And so this is when there's extremes with the pivot. They're either the largest or smallest element, which, like we talked about a couple of seconds ago, can really cause your sides to be off balance. But on average, it's linear arithmetic time, which is ideal for sorting algorithms, right? And also quick sort is in place, so it doesn't require extra memory to store intermediate results like some sorting algorithms do. So yeah, and also it's unstable, which, if you don't know what that means, we'll talk about it here in a few, right? So I want to talk about, if you don't, I kind of want to include this in here, so just to kind of give you a little bit extra of knowledge, So linear arithmetic time. So, like I've said this before in some of my other videos, this big O stuff, man, it's kind of like, whatever, man. Just like, tell me how you would use this, and like, I'm more concerned about people knowing how to use things in the proper situation than being able to spout a bunch of math at me. So yeah, but I want to explain it because you may be like, oh, linear, what is that? So the best example of this is used in school, man. Like, this is pretty traditional. So imagine you're in a library and you're going to organize books on a shelf using a divide and conquer approach, right? So the division of the books into smaller groups, that's your logarithmic time, right? So each time you partition the array, you reduce the problem size. And that's really what we'll talk about general rules of thumb here in a second, right? And so then what happens is when you divide those books into the individual groups on the shelf, you have to go into each book and you got to touch each book. You got to see each book to be able to compare it to the other one. And so you're comparing all the elements. So every element's being touched, right? Which is linear. Okay, and so these can be used as general guides for like these time complexities, right? So for algorithms where the input size is reduced, the problem size, think logarithmic, right? Think logarithmic time. And then for algorithms where you're processing every element, you can think of linear time. Okay. Now, is quick sort performant? Yeah, I mean, a sorting algorithm is considered. You know how I love my editing mistakes. when it has an average case time complexity of linear arithmetic time, which Quicksort has. And then the additional memory use should also be minimal, which is good because which Quicksort also excels at because it does everything in place, right? Like I mentioned earlier, you're not making copies or storing intermediate values. Everything's being done in place, so it's super efficient when it comes to space. Okay, so I'm going to do a little quick code run through of what we're going to be going through in the next video. I'm not going to go through it in depth. That's for the actual walkthrough. So so in our code, we pick a pivot. Like I said earlier, for ease of use and understanding, we just pick the last one. And then the partitioning, we just set up our left and right partitioning. And so, this, if you're not used to seeing like stuff like this, it can look a little intimidating, I guess. It's actually not that bad. Once I get in there and start walking through it, it's very clear. Don't be scared by the jumbledness of it all. It's very clear, and I write these things. I make sure that I'm writing these things. They're not fully optimized. That's not the point. The whole point is that you can clearly see how the algorithm works. You can reason about it. You can go through it. You can bring it to memory very easy, because in development, man, when you're doing development, a lot of times, your optimization is going to come later during refactoring. You just need to get the data structures in place. You need to get that basic functionality done so you can do your proof of concepts, right? And then you build from there. So that's what these things are meant to be. Right. So the elements being picked, we declare a variable, and then the for loop is going to iterate over the array, and it basically compares each element to the pivot. And then, smaller elements are moved to the left side. I is used to kind of track the boundary between the smaller and larger elements. That's why it increases. And then, at the end, we place the pivot in the appropriate location, right? And then we'll talk about the sorting and what's going on here. And also, this can look a little weird, but don't let it bother you. It's pretty straightforward. Now, in terms of usage, so Quicksort is faster than a lot of other sorting algorithms for most data sets, right? It doesn't require memory like merge does, so it's more memory efficient. And honestly, man, in most standard libraries and programming languages, the sorting, the built-in sort, most of those are implemented with Quicksort. So now, when do you not want to use Quicksort? Okay, so you don't want to use Quicksort if the input is known to be nearly sorted, right? So if you're dealing with a pretty predictable data set where that it's going to come in mostly sorted, and you're not going to have to do a lot of crazy comparison and like stuff to really get it in order, you're better off using something like insertion sort for things like that. Also, we're going to talk about stable sorting, right? So a stable sorting algorithm makes sure that if two elements have the same value, their relative order remains the same. Okay, so what does that mean? Okay, it's very easy, right? So say that you've got 3 students that have an ID and a grade. Okay, so looks like ID 1 and ID 3, they have the same grade, right? So student 1 and 3 have the same grade, but the value 1 comes before 3, right? So after a stable sort, we would have this, ID 1, ID 3. It's like, okay, well, I can't sort it based off of 90 because they have the same value, so I'm going to sort it based off of the next, and that's going to be ID. So that's what a stable sorting algorithm would do. Now, an unstable sort, it does not pay attention to that secondary ordering, right? It's just going to put them there. It may end up in order, it may not, okay? So, it should be clear where this is needed, okay? So this is an important applications where you need that secondary sorting, right? So where you've already sorted the data by one key, and then you want to go in and sort it by another while preserving your original sort, right? So sort by name, then sort by age. Very common, right? And then this is important too, think of linked records, right? So like logs, right? So where, especially like critical logs, like if you're doing incident response or you're looking at server logs or anything, those timestamps are very important, and that ordering can be very important. So once again, man, you really need to know the problem you're solving You need to be intimate with the problem you're solving to be able to apply the appropriate solution. And that's, dude, that's all about these theory things, man. You know, these theory things aren't for you to, you know, go through and just memorize a bunch of stuff and, you know, impress people in interviews. These things are practical, man. This theory stuff is practical. It teaches you, it teaches you how to. These problems have been solved, right? And you don't need to be writing another sorting algorithm, you know. And so knowing this theory allows you to work faster, and it lets you know how to solve problems. You know, lots of problems have already been solved, and a lot of new problems just require, you know, a reconfiguration of old solutions. You know, and that's why, man, this theory stuff and design patterns and stuff like that is very important. Okay. So it does have a practical use. All right, guys. Well, that's it for this. I'll see you in the next one where we do the code bit and run through that. If you have any questions about this stuff, hit me up. Help each other out in the comments. If you want respectable answers, ask respectable questions. And yeah, I'll see you in the next one.